kind of frequency range in this kind of an echoic environment, 75, that chirp is only 75 milliseconds long. But that's long enough to get 3 or 4 echoes off the walls, which means that the chirp is completely distorted by the time you record it. You can't use it. And MIT made a mistake trying to use it in their array. And in fact, if you look at their data set and try to correlate the chirps, they won't correlate. Or actually they will. You will get a correlation, but it's bogus. It's absolutely bogus if you visually inspect it. So you have to be careful about using common wisdom on things. It's like, oh, everybody uses a chirp, I should use a chirp. Not necessarily. There is another approach, and that's to use a pseudo-random noise pulse. And that's what's used on those swarming robots. But, again, they're using directional sonar and high-frequency sonar. High-frequency sonar won't work on a beacon because it's directional, and LORAN and GPS and things like that are absolutely dependent on an omnidirectional signal. So you can't do that with high frequencies. All right, what does a versine or haversine look like? There's one. That's the pings that you were hearing. Now they sounded a lot like an impulse because in my case they're only 6 samples long, so it's not much of a versine. But it's still gentle, and it actually makes a significant difference in the recorded waveform. All right. Then other issues about the pings themselves is how rapidly they can be issued. You notice that they were 50 or 60 milliseconds apart. They have to be far enough apart that they don't collide with one another. If all the beacons hit the microphone at the same time, you wouldn't be able to tell which one got there first. So they have to be separated out. The other is that I haven't figured out a reliable way to be pinging while the echo of a previous ping is still decaying in the environment, because those are self-similar signals, which is why correlation won't work. So you have to wait for the previous ping to die down below a certain level, like 60 dB, before you issue a new one. So these two things define the rep rate, the rate at which you can issue new pings, and the separation between them. Yeah, Paul?
I'm sorry, I forgot my question.
Oh, that usually works. If I talk long enough, people forget their questions. You were asking something about the...
oh yeah, about the waveform. So you're actually emitting like half a dozen of those cycles. Why is it...
No, I'm issuing one of them 30 times.
Oh.
So it's not several of those. It is like an impulse in that perspective.
And why is it important that it's all above the reference rather than going positive and then negative?
It turns out that the real world is going to force it to go negative. In other words, if this is 0, then this is supposed to be air pressure, and we're talking about positive air pressure only. That's impossible unless you're in a chamber and you're pushing on a diaphragm on that chamber. You cannot change the DC pressure of the room. That's barometric pressure, right? That's a weather phenomenon. So these little speakers can push the air out, and even in the little speaker could stay out, but the air around it would make up, and there would be this backlash behind it, and you would get a rarefaction behind that, no matter what you did. So it turned out that even if I did go up and down, all that did was to reinforce the rarefaction that was going to be there anyway. So I just said, we have that. Now another approach I took was to go up and stay there. That doesn't work either. The real world filters that as well, and it just keeps going. You get a greater compression, and it just rings like a square wave. And then I tried doing funny things like changing the rate that it falls down. And that brings you around to something called the system function. In other words, I could force this waveform to appear at the microphone by producing a really weird-looking waveform at the speakers. So why didn't I do that? Well, that system function changes based on direction. So the polar response, not only of the speakers but also the microphone, would make one system function completely different than one that was only 5 degrees away. We're talking about 3 speakers, and you'd have to have dozens of measurements. So I said, I hope I don't need to do that. Turns out it didn't. But the beauty of this is that, where did I had a little word here which somebody's going to, I said it was gentle to the system. The haversine has this quality that it doesn't, what am I trying to say? You don't need to know the system function. It doesn't ring a lot. It's narrow. It's just, it's gentle. I don't have to think of a better word. It works well.
Had a math teacher said well-behaved.
Well, I'm sure a math teacher would say that I was using the term incorrectly if I said well-behaved, but I like it. It sounds good. Okay, so what does this sound like? Well, you've already heard it, but here's, this is a different example. This is where the pings are at a fixed rate. The rep rate is 1 second. The pings are being issued every quarter second. So that's what was generated. But what was recorded in this example? And so there was a radio show going on, and then I walked over and clapped right at the microphones. And here's what was actually recorded. So can you see the, like in there, do you see the pings in there? They're going, you know, but real hard to see. And certainly the claps are 100 times louder than the pings. Okay, let's zoom in on it. Can you still see the pings? I mean, maybe there's one there, maybe. I don't know, I'm not sure. We'll see in a moment. There's the claps, really loud, and then the radio show in there, right? So if people say, oh, you just set a trigger and you look for what you're looking for, yeah, hope you find it. You know, this is the signal to noise problem. This is the problem that people had at the science place where they're complaining that, oh, those big windows mess up my infrared, or the shouting kids mess up my sonar. Yeah, deal with it. You know, that was my goal. I didn't like the bellyache. You know, I'm sorry. I haven't built a robot, so I don't have the camaraderie of saying, oh yeah, what a pain that is. I was going to like fix it. You know, make something that is designed to work in that environment, or designed to work in any environment. So, first thing is to do some filtering, high-pass filtering, which means cutting the lows. Cuts out air handling problems. The wind, not wind per se, but the rumble of your air conditioners and other things that are happening. And those can make it very difficult to set a threshold because the rumble causes the voltages to move up and down slowly. And then low-pass filter it, in other words, cutting off high frequencies to get rid of some things that could cause a false trigger. And for the high pass, I used what's called a matched filter, so I filtered it against what it was looking for, which is not correct because what the ping that gets issued is not the ping that gets recorded. I said, okay, I'll try it, and it works pretty well. It's wrong, though. It's not the right thing to do, but it's okay. The the high pass filter, I found to be absolutely necessary. If you don't get rid of the rumble below about 300 hertz, you have almost no chance of catching the pings. So this is what we recorded, and this is after it's filtered. So a lot of stuff went away, and it appears that maybe that really was one of the pings, right? And of course, the claps didn't go away because they cover such a wide frequency range that they can't be filtered out that way. The next big deal is waveform averaging. How do you improve the signal-to-noise ratio? At least a 50-year-old idea is just average things together. With waveform averaging, you have something that issues repetitively. And you record it, and you hack it up into pieces that are as long as the thing that you're looking for. You don't care where that thing is. You just hack up your recording that way, and you fold it up. You just fold it up. And I love waveform averaging because it's magic. It's just absolute magic. Because you don't care what you're looking for. So a Wiener filter would require, a matched filter requires that you know what you're looking for, which means a system function. You have to know what was going to be recorded. I don't know what the system function is, and I can't figure it out. If I did, if I rotate the speaker by 5 degrees, it's wrong. So that won't work. And then a Wiener filter goes the other way. It says, let's get rid of the noise. Let's get rid of everything else. That requires that you know what is everything else. Are people clapping? Are people shouting? And what is it that you're filtering out? With waveform averaging, you don't have to care about anything. You just hack it up, add it up, and what shows up is the stuff that's common to all of it. And it's used in electrocardiogram monitors in a sort of modified way. And to a small extent, whenever you say, well, that didn't work, let me try it again, in some sense, that's waveform averaging.
So about how many samples is your pulse duration going to be? I mean, as far as...
In my case, it's 6 samples.
6 samples, okay.
but there are 30 of them in the example that we were showing. That can vary. I found that if it's less than about 10, then there's so much noise in the environment that you're not going to get reliable results. And if it's more than 30 or 40, you get tired of waiting for it to finish. So I was fortunate that 30 seems to work pretty well. The waveform averaging improves the signal-to-noise ratio by the square root of the number of pings. So 30 pings would give me about a 16 dB signal-to-noise ratio improvement. Okay, another issue you have to deal with is compression, and that's basically how the claps and the shouts are dealt with. You could just do more waveform averaging, and they would go away, but it might take 1,000 pings to do that. But if you just compress the sound vertically, this is not data compression. This is not MP3 compression. You know, this is not a data compression. This is a audio dynamic range compression. If you do that, the shouts go away. The quickest and easiest way of implementing that is an outlier filter, a median filter, that just says, this data is outside my expected range, so I'll throw it away. The problem with that, be very careful with median filters because you don't know where the data is. You don't know what the data is. The ping could be, the ratio and the loudnesses from one beacon to the other could be so great that a median filter could throw away one of the beacons completely. So you have to be careful with that. It's not the panacea. I don't use a median filter. I use something else that I created on my own, which I won't tell you how it works because that's the only secret sauce I've really come up with here. Yes?
That leads me into what I was thinking. How important is it that your output hardware be exactly the same, and also the volume levels that are output at each device?
Good questions. I did choose speakers that were quite similar, but you might notice that they're not exactly the same. It is, if the wave shape that's coming off the three beacons are significantly different, then you may have to do some calibration to account for the fact that the crossing point, the trigger point for one is different than the trigger point for another. So but that can be dealt with. I didn't have to deal with that in this case because the transducers are all 2.5 or 3-inch transducers. All right. But if they were significantly different, that would be an issue that can be dealt with. What was your other question? Volume levels.
Volume levels.
Doesn't matter. The volume levels don't matter because you probably saw it before. Well, I'll emphasize it here in a moment. But maybe in one of the, I guess you didn't see it because I didn't put the robot over next to one of the beacons. But I have an example of that. So volume level is not important.
Well, I guess if you know
dynamic range is a problem. But once you've dealt with the dynamic range problem, then it doesn't matter how loud the beacons are. But you're on the right track. You're thinking about the right sorts of things. Let me put it this way. You're thinking about things that will bite you if you don't deal with them in your program. And I did. If you don't deal with that problem, then volume level will be crucial to you, and you will give up. So compression is a big help for that, because it kind of makes everything seem the same. Yeah. Okay? Yeah.
What's the difference between correlation and the time slicing that you're doing?
All right. Correlation, you can set as your thing that you're correlating to, you could set that to be your time interval. So I want to correlate to this time interval and hack it up by that time interval. It turns out that that's the same thing as just hacking it up and adding it up. But the difference is with correlation, you do a multiplication. You'd be multiplying by 1 in there, and all that additional multiplication slows down the program by about a factor of 10 when it's doing the waveform averaging. So correlation can be used for waveform averaging, but it's overkill. It doesn't provide you anything else, and it's just adding a few million more multiplications where you're multiplying by 1. It doesn't do any good. It's just inappropriate use for correlation. Correlation is where you take two signals and you multiply one by the other and you add up the results. That's it. That's correlation. And if the two signals are similar, then the result you get is a large positive number. If the two signals are dissimilar, you get a number that's either 0 or negative. And to the degree that they're similar, the answer is more positive. So, yeah, excuse me. Yes.
Have you given thought to how you could adapt this to a real-time continuous